So before we get into introducing vectors into this 3D environment, um, I want to talk a bit more about 3D space, and in particular, one of the most fundamental geometric objects that you can form in 3D space, and that is a plane. In particular, a simple plane. So what's meant by simple plane here is a plane that's either parallel to the xy plane, xz plane, or yz plane. So let me jump real quick. Let me remind you of these things. I'm going to jump real quick to this interactive figure that's in your e-text. Again, feel free to play around with this on your own. So remember, the xy plane is like our floor. That's this xy plane. And we notice with the xy plane that the z coordinates, pick any point in this plane, it has a height or z coordinate of 0. Any x values are allowed, any y values are allowed. Those are all wildcards. X can be anything, y can be anything, but z must be 0. And so if we specify, if we say, hey, collect all the points in 3 space whose x coordinate is whatever, y coordinate is whatever, but z coordinate is 0, what we'll get is the xy plane. Let me jump back real quick to this. That tells us the equation we should use for the xy plane. X is anything, y is anything, but we need z to be equal to 0. So the equation of the xy plane is just z equal 0. Easy, right? It's a fundamental object, and it has a very nice, easy expression for the plane. Think about what would be the xz plane. So again, here's the x-axis. Here's the y-axis. Here's the z-axis. So xz plane is just the plane. X can be anything, z can be anything, but y needs to be fixed at 0. I'm going to jump back to our little interactive figure here. X can be anything, y can be anything, but so this is the xz plane. X can be anything, z can be anything, but y needs to be 0. There you go. That's what that looks like. That's the xz plane. And it should have the form y equal 0. Jump back to that. This is y equal 0. Any point in space that satisfies, so any point x, y, z that satisfies this equation, y equals 0, gives me the yz plane. Again, that's how we plot structures like this. If I give you a function of x, y, z equal to some constant, you collect all the points that meet that criteria, and out comes some geometric object, in this case, planes. Equation of the yz plane, well, in that case, x should be 0, and the rest can be whatever they want. Let's take a look at that real quick. Back to my scene. And let's look at the yz plane. Try and visualize it before you see it. There is the yz plane. Any point on that has x equal to 0, and y anything you want, and z anything you want. No restrictions. Cool. Okay, so I just want to take a second and remember how this works. Any point satisfying this equation, y equals 0, generates the xz plane. That's how one way to generate objects in space. So just like in the 2D, if that's a little bit lost on you, that's okay. I have this example for you because this is something we should be familiar with. Equations in 2 dimensions. So here we're looking at any point x, y in the plane. It needs to satisfy, let's say we want it to satisfy a certain expression. Any point that satisfies, let's say, x equal 3, if we put that restriction, I want any point for which x is equal to 3, what does that give us? Well, x equal to 3 here. X is equal to 3 all the way on that line. Again, I don't care what y is. I just need to make sure x is equal to 3. And that gives me any point on this line then is fair game. That's x equal to 3. And so what this gives me, if I collect all the points that satisfy x equal 3, this gives me a vertical line. Vertical, if I have my coordinates laid out like this, vertical line at x equal 3. Remember how you give vertical lines? What about horizontal lines? Horizontal lines Again, I take all the points in the plane, and then I filter them. I say any points that don't have y equal to, let's say, -2, I'm going to get rid of those. I'm just going to keep the ones that have y value of -2. What does that give me? Think about it for a second. Should recall, this gives me a horizontal line. And my y value at any point will be -2. So let's go ahead and plot that real quick. Y value of -2. Any point, I'll use blue for this, any point on this line satisfies that equation above. And so that equation is what this line is. Or it gives me this line. So this line is y equal -2. This line is x equal 3. Is this helping? I hope so. Let's extend our planes now. So we talked about what are called the coordinate planes. So each one of these xy, xz, yz, these are coordinate planes. But we can give simple planes or anything parallel to one of those three coordinate planes. So this isn't we're not gonna step up too much. So quick problem we'll try here is find the equation of a plane parallel to the xz plane, but passing through the point 2, -3, 7. Ooh, okay, so that might sound like a tall order right now. It's not going to be that bad, though, I promise. Just bear with me. So the xz plane, that's this one. So the xz plane, remember, xz plane has just y equal to 0, right? Is our equation for that plane is y equals 0. Right, any x values are fine, any z values are fine. So these can be anything we want. This can be anything we want. But here, our y value is 0. That gives us the coordinate plane. We want one that goes through the point 2, -3, 7. So rather than y equals 0, our coordinate plane, I want to shift that over 1, 2, 3 in the negative y direction, and I want a plane there. Oops. So I want a plane that involves these lines going up, down, however I want. I want that plane that passes through y equal to -3. So again, any x values are fine, fair game. Any z values are fair game because I can head up or over in the x direction as much as I want and still be on the plane, but I need to fix my y value to be -3. So this plane, so solution is just y equal -3. As long as we put that restriction on our points x, y, and z, we force y to be equal to -3. What we'll obtain is this plane that passes through y equal -3, in particular this point. All right, that's it for this video. I will see you next time.